Hello, everyone. Thanks for coming. Hope you're not all completely doctored out, because I think this one's going to be pretty interesting. My name's Neil McAllister. I'm a reporter with The Register. That's a media publication, technology media publication out of London, UK. Some of you might know us, theregister.co.uk. Check it out. We're also a media partner with DockerCon. We've done that a couple times now, and that's because we really dig Docker. It's just one of the really interesting area for this industry right now, and it's moving so quickly. And I mean, just thinking about 2 years ago to now, we're talking about putting Docker into production. That's the big theme for this whole conference this time around. And these two guys are an example of that. You guys were at the last DockerCon, is that right? And they were presenting about like scaling a continuous integration system with Docker and containers. And since then, the last year, I should say, PayPal. We're talking about PayPal. And in the last year, they've been working on basically Dockerizing PayPal's entire PaaS infrastructure. This is the thing that thousands of developers build applications on, and they're Dockerizing the whole thing. And so without further ado, I'll turn it over to you guys.
All right. Good afternoon, everybody. I'm Ashish, and this is Mohit. So today, we are here to talk about how we integrated Docker into PayPal's PaaS. Last year, actually, we showed how you could use Jenkins, Mesos, and Docker to build a CI pipeline. And now a majority of our CI is actually running on Jenkins and Mesos. So we decided that the next logical step was to take it to our platform as a service application as well. So let me go over a few numbers as to what kind of scale PayPal operates at. So we have 165 million active customer accounts. We're present in over 200 markets. $235 billion in payments volume, and 12.5 million transactions on a daily basis. So our PaaS needs to scale looking forward in the future to meet this ever-increasing demand of operations. And what our PaaS does is that we run thousands of OpenStack VMs in multiple data centers. More than 3,000 PayPal developers are our direct customers. They depend on us for their daily application development, and they roll out to development, production every day. So what we see is we see thousands of deployments every day across both dev and production. So Docker is a natural way to boost our developers' productivity. Now, why is Docker so important to our platform as a service? So what we saw was that we have a combination of bare metal and VM-based infrastructure. So Docker provides the runtime workload portability across both these types of platforms. And once you create a Docker image, put your application code inside of it, you can be assured that the outcome is repeatable, that nothing will be different when you're deploying. We also have an overwhelming need to support multiple operating systems when we deploy and provision VMs. And so Docker is extremely useful in the sense that the host VM doesn't need to be a different OS. We can instead capture the OS flavor inside a Docker container, whether it's Ubuntu or RHEL. And our PayPal developers actually code in a variety of stacks, everything from Java, C++, Node.js, Scala, and even Go is something that they're doing now. So we need to support all these stacks, and with Docker, as we demonstrated with the CI and build pipeline, it becomes really trivial. One thing as PaaS that we notice is that once we flex up a pool of servers for any application in production, and eventually you're going to have to push some updates, you'll maybe flex down, flex up, go through repeated cycles. So things tend to change. Some packages, some SSL cert, some configurations here and there. So you'll notice a dependency drift, which is hard to detect until something really goes wrong. So with Docker, you can prevent these kind of application drifts. And one of the most beautiful features of Docker is almost the Git-like ability of tracking your image layers. So you know what has changed in a container, what layers have changed, and you can track the history as to when it changed. And our PaaS needs to rapidly deploy and roll back if things go wrong. So with Docker, that is extremely quick, as we've seen, because your old container is cached on the destination VM, so rollback is instantaneous. And as we saw with our build pipeline, we can actually For example, let's say I want to build a Java application. I can use a build container with Java and Maven in it for a Java stack, or I can use a build container with the Node NPM binaries for a Node.js stack and so forth. So our incremental environment upgrades are really not necessary for CI jobs. And so effectively, what we're seeing now with Docker is that there's really no difference between provisioning and deployment, because every time we are rolling out Docker containers, in essence, it's like you're rolling out an entire server, not just your application code with it. So that is a big, big boon for us. Now, let's go into the internals about how our PaaS orchestrates this Docker PDLC. So I'd like to say that our PayPal's PaaS is extremely complex, lots of moving parts, lots of very talented developers working on it, different teams. So I'm going to focus exclusively on the touch points where we integrated Docker. So what a developer would do normally is they would go into our PaaS, they would click a button, they say create my Java app or create my Node.js app, and we would provision a Mesos Jenkins CI for them. We would then create staging environments for them in VMs. We would create production pools for them, create load balancers, do all that stuff, set everything up for them. And now they're in a great position to start coding. They make a code change, they push it to GitHub, and then an SCM change triggers the Jenkins CI job, which would download that code, build a Docker application image from it, and push it into our private Docker registry cluster. I'll go into the details about how our registry operates, but I'll say at this time that we're using the open source V1 registry. We've added a few bells and whistles to it to make it more reliable, but that is what we're using because the V2 registry wasn't available almost a year before today. So, and neither was Swarm or Docker Compose or any of the nice and fancy tools that we have. But this is working for us, and we might eventually upgrade pretty soon. So our CI jobs actually push the application dev Docker images into this private dev/QA registry. And simultaneously, that image is now registered with our PaaS system. So what's the next step? A developer will now go through an iterative development cycle when they'll build, push, and finally they'll decide, OK, my Docker image, this final tag is now stable. I can roll it out to production. So the next logical step here is that we have something that is called a promotion service. What that does is that the developer tells our PaaS that, OK, this image needs to be rolled out to production. So what our PaaS does is that it notifies the QE and release engineering folks associated with that application. And they have to go through a chain of approvals before which they can certify that, OK, this image is good. We can now roll it out to production. And once that is done, what the developer has to do simply is click one button and say, roll out to production across multiple data centers. And what our PaaS will do is, via an Apache traffic server cluster, the destination application server pools would pull that Docker image from this pre-prod registry and roll out to production. Now, only the promotion service can push images into the registry, so it is secure. Nobody else can tamper with the images there. And we do have some validation at that layer that prevents any kind of tampering, any changing of the image layers, and it adds additional security checks. So this is a high-level end-to-end of how our PaaS kind of takes a Docker image all the way from dev to pre-prod to prod and deploys it across a production server pool. Now, how do we build and store Docker images? Just to quickly review the flow, there's your Jenkins CI from left to right. It uses the Docker CLI right now natively, and that pushes to the private Docker registry. And our Docker registry is backed by OpenStack Swift object storage. And it's not enough that you store the image in the registry. Now, the open source V1 registry, and I don't think even the V2 one, comes with an index. Because it's one thing storing an image, but how do you find it? How do you know what the tags are? How do you share your images? You can't. So we needed an indexing solution via which we could get that metadata quickly and easily. So we modified the registry to write the information to an Elasticsearch index, which is very widely used with Logstash and Kibana for analytics stuff. So it's kind of natural to also extend it for this purpose to get analytics about how many images are being pushed into our registry and all that data. So Elasticsearch is backed by OpenStack Cinder volumes. It is a block storage solution. So in case a node went away, you can easily reattach the volume and you're back in business. So now, once the data is there in Elasticsearch, you can easily use Kibana to create interactive dashboards, or you can directly call the Elasticsearch APIs, get the data out in whatever format we desire. So that covers the storage aspect and the indexing aspect. So let's review our open source V1 Docker container, which we took, and what we added to it. So we use Supervisor as the process manager. It already had Nginx and Gunicorn, so we just made Supervisor control those processes. We added log rotate so that we didn't have to clean up after the logs. We added the Elasticsearch plugin to the V1 registry for indexing, so that once a Docker push has completed, that plugin would then write the metadata associated with that image into Elasticsearch. And we also use the open source Swift plugin for storage, so all your image layers are actually going to Swift. And we added basic auth at the Nginx layer. We have an Ansible playbook for setting up the registry, and all this code is available on GitHub, and we'll give the link a little bit later in the slides. We made it highly available. We could scale horizontally because we can just put a bunch of VMs, each running one registry container behind a load balancer. And to solve the chicken and egg problem, like how do you deploy a Docker registry container if you don't have a Docker registry to start with? So there's a Docker load command in which you can just launch these instances for the very first time. So that covers the registry. Now we'll dive a bit deeper into how, or what challenges rather we faced when we set up the index. So at PayPal, we're extremely strict about security. That means our production firewalls block almost everything. So you can't do multicast clustering of Elasticsearch nodes in production. And we noticed that when a node went down, you had timeout issues, split brain problems. So to solve all those issues, we use Zookeeper as the discovery mechanism for the Elasticsearch nodes. There's a Zookeeper plugin. That's also open source. And then what the registry would do is we wrote a Zookeeper transport plugin for the Elasticsearch Python client. So the registry, which is Python code, it would basically use that to discover the Elasticsearch nodes dynamically. So we don't have to hard code a bunch of Elasticsearch node IP addresses all over the configuration files. So both the registry and Elasticsearch would go to Zookeeper and find each other. So the other problem, of course, as I mentioned, is that the Docker Hub or index is really not open source. And that is one big reason behind this. So finally, Cinder is the persistent solution, as I mentioned. So I think I pretty much covered all the points here. Now let's look at the cross data center view. Finally, if we put all these pieces together, how do we actually deploy in production, right? So as you can see here, we have our bunch of registry VMs. We have Elasticsearch. We have Cinder and Swift as the storage solutions. We have Zookeeper for discovery. So now we have our kind of fully open source registry setup good to go. And these are our multiple data centers that we want to deploy to. Now, each of these data centers would be running Apache Traffic Server caching servers. And they're all behind a load balancer. So the way it would work is that firewalls separate everything. Then they cannot see each other at all. So how do the application servers get hold of the Docker image from the pre-prod registry and roll them out into the respective data centers? So they would go through the Apache Traffic Server cluster. And the Apache Traffic Server clusters, in a one-way operation, would do a Docker pull against the load balancer fronting the Docker registry. So that is how we avoided really the pain point of maintaining the entire Docker registry cluster in every data center, which is very hard to maintain and debug and troubleshoot. So we like to maintain one instance of it all, make it really highly available, and just use caching to actually deploy and roll out everything. So this is where I think Mohit will take over. He will dive a bit deeper into the Apache Traffic Server internals, and then he'll also go through the local developer workflow and the demo. Thanks.
Thank you, Ashish. Is it working? OK. So in this slide, we can see that we are using Apache Traffic Server as a caching proxy and also as a content delivery network for the Docker images that we have. And in the next slide, we're going to dive a little bit more deeper into how the traffic server actually works. So once the deployment is triggered through the deployment system, all the application servers in production will basically initiate a Docker pull operation against the traffic server endpoint. And the traffic server endpoint basically resolves to the local ATS cluster to the data center. And then the Docker daemon will basically establish a HTTPS connection with the traffic server. Once the traffic server gets the request, it will basically terminate the SSL and then inspect the request to check if we can serve it from the cache or not. If we can serve it from the cache, we just serve the cache response and then move on with life. Otherwise, the traffic server will basically connect to the origin server, which in this case is the Docker registry over another HTTPS connection. Once the Docker registry comes back with the response, traffic server basically caches the response. And at this point, I think I'll go into even more detail into the caching policy that we use. And to understand the caching policy, we have to understand how a Docker pull operation really works. So a Docker pull operation basically involves multiple HTTP GET requests between the Docker daemon and the Docker registry itself. And during these GET requests, two types of data gets exchanged. One is which I will call like static data, another one is dynamic data. So static data being your actual image layers, which are immutable and they never change. And the dynamic data being the data about the tags that you have for your repository. And that data can change over time, right? And you don't really want to serve that from the cache all the time because you will lose visibility into what's new in your Docker registry. So what we do is we basically serve all the static data, which is the image layer data, all the time from the cache, and we serve the tag data always from the registry, except in one scenario when we actually lose the connectivity between the traffic server and the registry. And by doing so, we are basically increasing the availability of our systems. So once the caching is done, we move on to the header rewrite plugin. And the header rewrite plugin basically modifies the X Docker endpoints header that is set by the Docker registry. And this header is used by the Docker daemon to actually make future connections to the server, the registry server, basically. And we modify this header to be the value of the traffic server endpoint so that the future traffic from the Docker daemon can still flow through the traffic server. And if you don't do that, then the Docker daemon might try to connect directly to the registry, and that might fail because you might have firewall restrictions. And once the header rewrite plugin does its job, the response actually flows back to the application server. And that basically completes a Docker pull operation end-to-end. And we also use Ansible again here to manage our traffic server instances in production. Now, I would like to move on to the development environments. And I would like to touch upon some of the pain points that we have with the development environments. The first one, I guess, is building an application is like really hard. I mean, because of the tool chain that is involved when you want to like build the code. Also, the development environments across the developer laptops are like snowflakes because each developer might have their own preference of the tool that they are using. Some developers want to use a newer version of the tool, and some might like stay back with the older version. They might never update. And because of these version differences, some creepy bugs can appear in production, which are like really hard to track down. Also, development environments should be self-contained. A good example of that can be most of the developers do their daily development on a Mac or a Windows laptop, and the code might run on a RHEL server or a Ubuntu host in production, right? And sometimes what happens is whatever you are working on might not get thoroughly tested, right? And then some binary compatibility bugs might appear in production because of that. Also, some development environments makes it like really difficult to simulate QA or production-like setting right from the developer laptop, right? A typical dev test cycle looks something like this. So a developer basically starts working on a feature, and once he's satisfied with it, he basically tests that on his laptop in a very limited fashion, and then he wants to deploy that code to to a QA server where the code can actually interact with other QA namespace services. And to do that, he has to basically check in his code to the Git repository or a source control system, and then the code gets built by Jenkins. And then finally, the built artifacts are pushed to our artifact repository. And then finally, the deployment system deploys the code to a QA or a staging server. And then the developer can actually see his creation in action, like interacting with all the other services. And then he gets some feedback, and then he goes back to his routine development. And this dev test cycle can take anywhere between 5 to 20 minutes, and sometimes even more, depending upon what kind of application stack you are using or what kind of environments you have at your organization. And this really hinders innovation. And so to solve like these problems and to minimize the churn of this dev test cycle, we decided to use Docker to create developer environments. And we chose the Docker Compose project and the Boot to Docker project from the Docker team to do that. And with these developer environments, you can run the source code that you are working on your laptop as a dev namespace container or a QA namespace container. And when your code runs in a dev namespace container, it can talk to all the dev namespace services. And if it is running in a staging container, it can talk to all the staging namespace container services. And that really allows you to like minimize this dev test cycle churn that I talked about, and like do really fast iterations on the feature that you're working on. And with that, like let's move on to a live demo. So during this live demo, we are going to cover like 4 things. One is we'll run a simple Kraken.js application, which is a Node.js framework that PayPal has open sourced inside a Docker, which is very simple. And then we'll do a live debugging of that application. Then we'll see how we can like work across multiple branches. And then if we'll have time, we'll try to simulate QA environments from laptop. So, okay, so this is the homepage for the Kraken.js framework that PayPal uses nowadays for a lot of its front-end applications. And this is the a sample GitHub repository that I created for this demo. The link of this repository will be in the slide, so you guys can check it out later. And in interest of time, what I've done is I have checked out the source code on my laptop already. So we already have the source code. And this is the Docker file that I created for the base image that we will use to run the application. It basically installs a bunch of build tools and Node and NPM dependencies and configures a bunch of stuff. And then this is the very basic Docker Compose file that we will use. So an important point to note here is that this volume section here. So what we do is we basically mount our developer's source code repository inside the container, and then when the Docker container will run, we'll basically run the source code that is right now on the developer's laptop and not the one that we have already burnt in the image. So that way you can like do really quick iterations. And this is a sample model that we have. And in this model, we are basically we'll basically echo master on the page whenever we'll run the application, right? So without further ado, I'll just start the application. So I'll use the docker compose command and say docker compose up. So it is basically going to create the container, and the container is up, and all the processes that we spawned inside the container are also up. So we use supervisor, as you can see from the logs, to launch all the processes inside the container, and supervisor basically acts as the primary process in the container. And we launch Nginx, and the Node.js is obviously the application, and the node inspector is the debug utility that we will talk about. So once this is launched, we can basically go to the application, and we can see that it prints hello master. Very basic stuff, nothing fancy. Now let's debug the application that is running inside the container. So we are running the debugger on the port 8080, and we use the node inspector module that the NPM provides to do this. So once I visit this URL, you can see the debugger in action. And we have basically put a breakpoint on this in this controller so that whenever the server will get a new request, this breakpoint will be hit. So let's refresh this page now. And as you can see, the page basically spins here. And the response doesn't come back from the server because the debugger has halted the execution. And at this point, you can basically inspect various variables that you have in the code, and you can step through the code and stuff like that. And whenever you're satisfied, you can resume. And so this is like right now running on your laptop, but since this is a Docker container, you can run the same container on a different server and still get the same debugging abilities, right? So, which is kind of like very helpful. Next up, let's do this. So right now we are on the master branch here. What I'm going to do is I'm going to check out a different branch, and I will try to do a regression between a feature that I'm working on. And in this hypothetical feature, what I'm going to do is I'm going to go back to my model and change the name that I want to show on the screen as feature 1. And since we are going to run 2 containers together on the same host, to avoid port collisions, we'll basically also go and modify the ports so that we don't have a port collision when we start the application. And then what I'm going to do is I'm going to start the application again. Now, one more important thing here. So when we started the other container, the Docker Compose basically named the container as docker con demo _ web _ 1. And the way Docker Compose does that is it takes a directory name of your project and then use that as a prefix to your service names. And in Docker, you can only spawn, when you're starting up containers, those containers cannot have name collisions. Now, if I just do a Docker Compose up here, my application won't start because there will be a name collision. And to avoid that name collision, what I'm going to do is I'm going to use the -p, which is the project option, which the Docker Compose provide, to tell that I'm basically working on a feature 1 branch. And when you launch the container, please prefix that with this. And I'm going to basically start it like this. And as you can see here, it used the name as feature 1 web 1. So the advantage of this is now you are running 2 different versions of your repository as 2 separate Docker containers on your laptop. And even the feature 1 branch container is now up, and we can actually go and visit that in the browser. So I'm going to hit the application, which is running on port 90, and we can see that it's feature 1 now here. And we can do the same debugging exercise that I talked about earlier. So again, I can open the debugger, and again, I can hit the breakpoint here. And if I go and refresh the page, the debugger will come into action, and you can do stuff. So with that, you can debug 2 different versions of your applications, like on different branches together on your laptop, which is I think very, very helpful when you're trying to find out which commit caused the bug and what changed like really in the code. So one important thing to also note here is that in the Docker Compose file, you will also see that I'm using the source node modules as a volume. And those of you who are like familiar with node modules, I mean, these concepts also apply to any other like stack like Java, where you might want to like mount your Maven repository. But this node modules directory is basically the one which gets all the dependencies that your application has. And we also mount this as a volume like a Docker volume. And the reason we do this is to avoid these 2 different containers to step on each other. Like for example, on a master branch, I might have version X of some dependency. And on the newer feature branch that I'm building, I might introduce a version Y of my dependency. And if I don't do this, then they will basically step on each other, and then you might run into crazy bugs. So doing so also allows us to like avoid those situations. So with that, I think we'll go back to the presentation. So this is a typical dev configuration which like developers use. And as you can see here, that we have like more volumes that we mount to avoid polluting the actual container. And the sorry, not the container, but the Git repository that the user has, because these are some of the artifacts that are generated at runtime. And similarly, this is a QA configuration with the similar nuances. The other thing that I wanted to mention is you might be wondering, why can't I run my application in the QA mode directly on my laptop? Well, in some cases, the applications might be simpler, and when the application runs in a dev mode or a QA mode or a production mode, you don't really have any external dependencies, like a external logging daemon that the service might be expecting, or a let's say a service discovery daemon that you might be expecting to run on the QA server, right? If your applications are very simple, then you don't really need this kind of setup. But when your applications and your deployment environments are really complicated, these really help, because you can now start your application, which is supposed to run on a rel box, and expect a logging daemon, which is, let's say, very native to Linux. You can run all of that on your Mac or a Windows laptop. Whereas if you don't use Docker, you cannot really do that, and you cannot achieve all these benefits. So these are some of the links that I have put in. We have the link to the demo that we just saw. We also have the link to the changes to the Elasticsearch index that we did at PayPal. And we also have the Ansible setup for the private Docker registry that we just discussed. So please visit them and give us feedback, and we can take it from there. And with that, we would like to conclude. Thank you.
So I think we'll just go ahead and start with questions if there are any.
Thank you. Great talk, guys. So just had a quick question. I know you're using Apache Traffic Server to be able to use caching, but how are you managing your, I know you mentioned it before, just trying to understand, how do you manage your Docker registry? Where is it located? Do you have one version? Do you publish to that one version? How do you manage that?
So we only have one source of truth, which is the Docker registry, so we only have one replica of Docker registry, and then that sits in one of the environments. But in all the other data centers, we just run the Apache Traffic Server cluster. We don't have the mirrors, which you might be referring to. And we just use the Apache Traffic Server to cache the images. But all the images basically come from one source of truth.
How you doing? Great presentation, Short Fidelity. Quick question. How do you handle 3,000 developers? How do you handle project intake and self-service? Didn't really get into that in the presentation itself, but I think it's a critical piece that probably does live in your stack somewhere.
You want to take a stab at that?
Yeah, so we're not just two developers managing, it's an entire company, right? So what we typically have is, for every stack, we have a dedicated team. Like for Java, Scala, Node.js, we have infra teams that maintain these stacks and provide support to the developers consuming that stack and deploying on those stacks. So those teams would maintain the base Docker files. We as PaaS would actually give just the bare bones Ubuntu or RHEL base image to these infra teams. They would build on top of it, create the individual Docker base images for every stack. They would then help the developers consume that, write applications, and then where we come in is during deployment, during provisioning as PaaS, right? So we give everybody the tools to deploy and develop, and we take care of the most important back-end aspects, which is how do we deploy your instance, how do we make sure it stays up, how do we load balance, if something goes down, how do we bring it back up, remediation, etc. So that's where kind of we come in. So there's many people involved here, hundreds of people. So I think that answered your question.
For a local dev environment, do you like recreate Docker image after each code commit change, or like?
So that's a good question. So you don't really have to, because as I showed you so as we can see from this slide or any of these slides, you basically mount your source code inside the container. So, and then your init script of your container, which is this guy, can build your application within the container. So if only your application bits are changing, you don't really have to build the container to just test it, I would say. But if you want to like publish the image to the Docker registry, then you might want to like rebuild the image, because then you want to actually copy the code from your host into the image.
So since you mount your, if I saw this right, if you mount your dependencies like your node volume or node packages as a volume, right?
Mm-hmm.
So do you ever run into any reproducibility problems if you might update a dependency?
I didn't get the last part.
Do you ever run into any reproducibility problems, not being able to reproduce a particular build because you update a node package?
So yeah, so with Node, it's a little bit tricky all the time, right? Because a lot of the Node modules, they don't use like static versions, they use dynamic versions. And even if you like take out Docker from the picture, if you're just doing local development on your laptop, you might run into the same reproducibility problems, right? So adding Docker to that equation like doesn't really make it worse, I would say. So I think that's a general pattern of how like Node developers like to work, because they want to always get the bleeding edge version of the modules. So did that answer the question?
Yes, thank you.
Okay.
Thank you for your presentation. In the slide, sorry,
Oh,
over
okay.
here. In the slide where you diagrammed Apache Traffic Server, it seemed to indicate you were storing your Docker images in Cinder. Is that correct, or are you storing them in Swift?
So we use the traffic server's cache directory is mounted on a Cinder volume. Yeah, not an object store. We are using the block store.
Did y'all have y'all found that the Swift object store was not performant enough, or to hit directly to store images in Swift and directly pull?
Yeah, I mean, we did some benchmarks and we found that using a Cinder volume was much more performant compared to the Swift object store.
And
Okay.
we use Swift primarily for the registry, because it makes more sense there, because then the registry can directly write the image layers to it, whereas this is more of a caching server. It's like doing transparent proxying. It's a proxy cache is the best way to put it, right? So
Right.
we would have to actually write a driver for it to store into Swift, right? Whereas with Cinder, it's block storage. We attach it to the underlying VM, and you're good. You don't need to touch the ATS code base in any way for it to store data or the image layers into it, right?
I guess I was a little surprised that Swift needed a ATS, or would have needed something like ATS. My second question, have y'all experimented at all with putting ATS on a Docker container for like data locality with basically moving your image cache to your Docker machines?
So, I mean, so you're saying like, do we run Docker daemon on the ATS servers?
More like running ATS servers as containers on your Docker daemon servers on like your Mesos, inside of your Mesos cluster.
I mean, we've thought about it, but in the initial version, we didn't do that. We are not managing the ATS cluster with the Mesos right now. We're just running them as the sole process on the host.
There's nothing stopping us from doing that.
Nothing,
we
yeah,
could do
exactly.
it. So it's just, we just haven't got to it yet. So
Thank you.
Anyone else? I think I'd just like to ask, I mean, you've given us a ton of information up here. I always like to ask, what's next? You know, you mentioned maybe thinking about moving to the V2 registry. It might be something you do. Is there anything specific that you can talk about that is, you know, what you're working on now, or any particular pain point that maybe isn't yet worked up as well as you would like it to be?
there's actually a lot of new stuff that was announced in this DockerCon, the Docker Swarm, Docker Engine, the open container format. So it will take some time for us, because we already have an existing setup that works. So we just have to ingest all that information, see what works for us, and then integrate it into what we have. So that will take some time to do. So that is one pain that everyone has to go through, of course. So.
Doesn't surprise me. Anyone else? All right, I guess we'll wrap it up. Thanks a lot, you guys.
Thank you.
Thank you.